Now talk about the two very important series, what we call the Taylor series and the Maclaurin series. Um, the Taylor series of f at a. So when we talk about Taylor series, we always talk about a center. So it's centered at a. Uh, so there's a center at a. Okay. Uh, Taylor series of f at a is we write this, so this is a formula, so it is fx equal, so this is a series representation, n going from 0 to infinity, f n, that's the nth derivative, evaluated at a divided by factorial n, and then x minus a to the n. So you can see that's the format, so you can see that n appears in 4 places, in the index, and 3 places inside, and then a appears in 2 places. Okay, so that is the expansion, what we call the Taylor expansion of a differentiable function. So the condition would be whether the function is differentiable. If the function is differentiable, then we can write this expansion. This is what we call the Taylor expansion. So I'm going to call it equation number 1, formula number 1. And then so if you write few terms, so what happen if you apply n equal 0, you get the function evaluated at a, if a, and then what happen, the first derivative evaluated at a divided by factorial 1, which is 1, and then x minus a to the 1 plus, and then we have f second derivative evaluated at a divided by factorial 2, which is 2, x minus a squared, like that. So you can see these three numbers are always the same. So you can see this is second derivative, this is 2, that is 2. So like that. So then we have 3, 3, 3, 4, 4, 4, like that. So that's the format of the what we call the Taylor expansion. Now if a equals 0, we call this is a Maclaurin series. That's a very special case when a equals 0. So if we have a equals 0, we get what we call the Maclaurin series. Okay, that's a very special situation. We put a equals 0. So it is called a Maclaurin series. So it is very interesting. The Maclaurin series came after the Taylor series. The special case came after that. That's normally does not happen in mathematics. It goes the other way around. But this time it came after. So it is fx, it is equals to the Maclaurin series. So it is n going from 0 to infinity. What happened now? We simply evaluate at 0. So we put, instead of a, we put 0. And then factorial n, no changes. This is x n because a equals 0. So that is the Maclaurin series. So what happens? So we have a simplified form, so which is f0, and then f prime 0 x plus f double prime 0 factorial 2 x squared, like that. So that is the Maclaurin series. So I need to remember the formula. So we use this. So what happen is, you can see we don't have to do much. We just need to find the derivatives and plug in there, and that's going to give you the formula. So if you have the Taylor expansion, remember the format, the x minus a term. Okay, x minus a term. Here we only have x term because a equals 0 when you talk about the Maclaurin series. So when you have Maclaurin series, you would remember that a equal 0. And then the third formula is what we call the nth degree Taylor polynomial, because these are series. These are infinite series, is going to forever. And then what can happen? We can truncate this at a nth degree term. Then we get what we call the nth degree Taylor polynomial. So let's talk about that. Uh, so nth degree Taylor polynomial. Taylor polynomial. So this is a polynomial. So since it's a polynomial, what's going to happen is, so you're going to truncate at the nth degree term. Okay, so it's a polynomial. So let's write it. So we use a notation for that. We call it a Tn x. Some people call Pn. Since a Taylor polynomial, we use a Tnx. So what happened? We use a sigma. We use a different index this time because you have to stop at n. So you can use the same index, same for the index. So we have n. So what happened? It's the same formula. So it is fn. It's not fn now, fk, because the index is k. So k uh, evaluated at a factorial k x minus a to the kth power. So this is what we call the nth degree Taylor polynomial. So let's write a few terms. So if you write the first few terms, it's very similar. So it is fa, no changes. And then this is f prime a over factorial 1 x minus a, like that. So what we can do, we can write until we see the nth degree terms. That means fn a over factorial n x minus a to the nth power. So that is the nth degree Taylor polynomial. So if you say third degree, you're going to go up to third degree. So that means you need to calculate the third derivative. Okay, so that's the formula. So we have this. So and then the last formula that we need is what we normally call the Taylor inequality. Okay, so so let's write this notation. So let's say let Tn be the nth degree, uh, Taylor polynomial, nth degree Taylor polynomial, nth degree Taylor polynomial of f at a. So a is a center. Then what we can do, we can write what we call the remainder. Then we can write remainder, which is r n x, because it's a function of x. So which is just a difference between fx and the nth degree Taylor polynomial, because you're going to truncate at the nth degree. So then there's an error. That's what we call the remainder. So then what we have, what we call the Taylor inequality. So let's try the Taylor inequality. Taylor inequality. So what it says that, so this is an interesting result. So it says that if the nth derivative, if the n plus first derivative actually, n plus first, so you're going to go to the next one, n plus first derivative is bounded by some number m on an interval, centered at x minus a, which is away from d, away from that. So d is the radius in this case. So you're going to go d away from a. So that means, so this is a. So what we're going to do, we're going to go d away from that. Okay, that's the distance we consider. So now on that, the derivative is the n plus first derivative is bounded by a number m. So if this is the case, then what's going to happen? Then you can show that the error term is bounded by m divided by, and you can see this is very similar to the general term. It is n plus first now, n plus first factorial absolute value of x minus a to the n plus 1. So you can see it's very similar, That's the next term for any x in that same domain. So that's what you can see, this is the same domain. So what it says that if this is so then your error is bounded by that, and also if this error goes to 0, so this is the most important part. If this error term goes to 0 as n goes to infinity, if this error goes to 0 as n goes to infinity, then the Taylor series converges to f. Then the Taylor series Taylor series converges to F. So that's very, very important, because we know there's a series, but we don't know whether it's going to converge to F. But it says that if the remainder term goes to zero, if the remainder term goes to zero when n goes to infinity, it says that the Taylor series converge to F. Okay, and that's it. Those are all the theories. So let's look at a few examples, starting with a uh, Taylor series of a general term. So let's look at this now. Uh, so as the first example, let's do this. So let's say find the Taylor series for. So find the Taylor series. Find the Taylor series. Find the Taylor series for. Let's say fx equal e to the 3x at let's say a equal to some number. Okay, so we have a function and then we have a number, Sena. So we need the Taylor series. So what we do, we can look at the several derivatives. So we're going to start with that. So we're going to say fx that we know, which is e to the 3x, and then what we're going to evaluate few derivatives. So let's say first derivative, so it is 3e 3x, and then the second derivative, so we can take one more 3, so it's 3 squared e to the 3x. So if you look at the pattern, you can see that the general nth derivative gonna looks like you're gonna take 3 to the n, because every time you get a 3 and then e to the 3x. This says that if you evaluate this derivative at 2, that's a, it is 3n e to the we're gonna get 6 because it's 3 times to 6. So that is the nth derivative. So now what we can do is we can plug into the formula. So if you plug into the formula, then we can write the Taylor series. So we can write the Taylor series. So we can say just T. So that's the Taylor series. So we can write this is sigma n going from 0 to infinity, f n, in this case 2 divided by factorial n x minus 2n. So let's plug in. So which is n going from 0 to infinity. We find this is 3n e to the 6 divided by factorial n x minus 2 to the n. So what you can do, we can take e to the 6 out as a factor. So if you do that, you get e to the 6 sigma n going from 0 to infinity, 3n factorial n x minus 2 to the n. So that's what you get as the Taylor series for this. So it's not a difficult calculation. And also, so we can show that this actually going to converge to e to the 3x, because you can show that you see that there's a factorial term there. So that says that in the ratio test, this is going to converge. And then you can show that since the derivative is bounded in a bounded domain, you can see that if you pick any bounded domain, you can see that the derivative is bounded. If the derivative is bounded for any fixed x, this gonna convert. The error goes to 0. So it's very easy to show that. So that means this is this series is gonna converge to e to the 3x. Good. So let's look at another example. So let's look at this problem. So let's say find the Maclaurin series. So be careful when you say Maclaurin series, we know that a equals 0. Okay, Maclaurin series, that means a equals 0 of the function sine 3x. So we have a sine 3x function. So what we're going to do, we basically just need the derivatives. So let's do that. So we're going to start with fx, which is the function sine 3x. What is the first step? You can evaluate at 0, a equals 0. So if you evaluate at 0, we're going to get sine 0, which is 0. And then we can take the first derivative. So if you take the first derivative by the chain rule, sine become cosine and multiply by the derivative of 3x, which is 3, so that means 3 cosine 3x. And then we can evaluate this at f prime 0. So we can plug in 0, so which is 3 cosine 0. Cosine 0 is 1, so you get 3. And keep doing it. So if second derivative, so you're gonna get now it's a cosine. You know, derivative of cosine means sine, negative sign. You get another 3. That means negative 3 squared sine 3x. And again, we can evaluate this at 0. So you get negative 3 squared sine 0, which is 0. So keep doing until you see a pattern. We don't see any pattern yet. So let's say third derivative, which is the third derivative. Sine means cosine. You get another 3. So negative 3 cube cosine 3x. Now we can evaluate this at 0. So you get negative 3 cosine 0 means 1, so you get that. So we still don't see a pattern, so let's go for the next derivative. So we're going to go the fourth derivative. So it is cos, that means negative sign. With this negative sign, it becomes positive. So it's a 3 to the 4 sine 3x. And if you evaluate this at 0, you can see this is 0. Now you can see that this came back to sine. We start with sine. That means this is going to go in a cycle, except you're going to increase the term in front. So if you get the 4 derivative, you get 3 to the 4. And then you can see the sine. Also, there's a sine convention. So if you plug in these to the series, so what we're going to do now is we're going to find this into the series. So the Maclaurin series. So we have, and also we can notice that you can see we only have the terms with odd terms, so odd derivatives. So the first derivative term is there, third derivative term is there, or everything else is 0. So you can notice that. But let's write the general term, a general series. So it's f0 and then f prime 0 factorial 1 x, and then f double prime 0 factorial 2 x squared, f triple prime 0 factorial 3 x cube, like that. So let's plug into those terms. So f0 is 0, and then we have f prime, which is 3 over factorial 1 x plus, and the next one is we get negative 3 squared over factorial 2 x squared, and then positive. Actually we made a mistake here. So you can see this is actually 0. So you don't get a square term, which is because second derivative is 0, so you get 0. And then the third derivative is there, which is negative. You have 3 cube over factorial 3x cube, and then you have a 0, and then you have a plus, so like that. So let's write the first few terms now. So if you write the first few terms, so you're gonna get, and then actually we can write the next term. So what's gonna happen the next term if you look at the pattern? So you can see next term going to be because the sign change. So you start with the plus and the minus, and then next one is a plus sign. So we have so if you write it, it's a 3 to the 5th a factorial 5 x fifth, and then a 0, and then a minus sign. So like that. Now we can collect those terms. We collect those terms, so then we're gonna get this one. So we have the series. So you can see sine 3x, which is the expansion of 3x. So that's the first term we get, and then minus 3 cube over factorial 3x3, and then we're gonna get 3 to the 5th factorial 5 x to the 5th, and then minus, like that. So now what we can do is we can write this as a series expansion. So you can see you only get the odd numbers. So that means we need to find a way to write odd numbers. So, and also there's a sign change, that means there should be a negative term. So I'm gonna leave it like that. So you can see, you can write odd number like 3. How to write odd number? You can write odd number in two different ways. One is you can write tn minus 1, or you can write 2n plus 1. So depending on how you want to write it, it just change the index starting value. So let's use 2n plus 1 notation. So you can see it is 3 to the 2n plus 1 and divide by the same one. So it is divided by the same one, the factorial of the same number, and also this is x to the same number. So those three numbers are the same, but as a factorial. Now you can see what is the starting value. You can see you should get 1. That means you have to start with n equals 0, and then also you should get a positive term in front. That means you start with n equals 0. That means this is n, because if you start with a negative one, it should be n minus 1 and plus 1. So that is the summation for the uh, Taylor Maclaurin expansion. And then also you can see that and then also we can write this one. Okay, so also notice that the derivative. So the f n plus 1 derivative, um, the absolute value of that, and you can see this is a 3 to the n. So we can see this is simply there should be a sign term. So but since we take the absolute value, we don't need that, so we only have a 3 n plus 1 and some sign term, but we know the sign is always in between -1 and 1. So this one is always in between -1 and 1. So that means this is less than or equal to 3n plus 1. So that is the m that we are talking about in the Taylor inequality. So now you can see for any fixed x, so in fixed x, so we can see for a fixed x, you can see the error term. So what's the error term? That's the next term. So that's what we learn. So that means you can see that the error, the absolute value of error, which is going to be 3n plus 1, which is a fixed number, divided by n plus 1 factorial, and this is x minus a, in this case x. So you can see x is a fixed number. So and we need the absolute value of that, and you can see when x is fixed, because of this factorial term in the bottom, you can see this gonna go to 0 as n goes to infinity. So that means so the Maclaurin series converges to the function. So the Maclaurin series converges to sine 3x. So that means we can write this one as, until then we can say whether they are equal. So now because this error goes to 0, you can say this is exactly equal to the series that we got. Good. So it is 3 2n plus 1 over 2n plus 1 factorial x to the 2n plus 1, and you can see it converges for all. So for all, that's the interesting part, for all x, because if you have any x, this is gonna work like that. So that's the interesting part. Good. So but if you look at a problem like that in exam, what's going to happen is we normally ask you to find first few terms, like first 5 terms, first 3 terms, like that, because there are a lot of things involved in most of the situation. Okay, now since we know the Taylor Maclaurin series of this one, if you want to find another series, you can make life much easier. So this is a kind of problem that we can ask next. So let's say, how about um, find the Maclaurin series, of, let's say, x cube cosine, let's say 3x squared or something like that. So, but you already know what is the Maclaurin series of sine 3x. Now we are asked you to find the Maclaurin series of this one. So what are you gonna do? You're gonna see the connection, whether you can get this one using any derivatives or integrals or something like that. But we notice this one. So our starting point gonna be, you can see this cosine and also the 3 in there. So that means, so we're gonna start like this. We know that the cosine 3x is simply the derivative of sine 3x. You know that if you take the derivative of sine 3x, which is 3 cosine 3x, since you get the 3, we divide by 3 to match it. So that they can cancel, you nicely get cosine 3x. So what we simply do is, now, since we know the series representation, we're going to put it there and simplify. So we're going to say 1/3. So let's take the derivative here. So we're going to plug in the first few terms. So it was 3x minus 3 cube factorial 3x cube plus 3 fifth factorial fifth x fifth minus, like that. You can also use summation notation. So let's take the derivative, but once you take the derivative, what's going to happen now? So it is 1/3. So we can take the derivatives. So this is simply going to be 3 because it is derivative. And then here it is 3 to the 3 factorial 3. If you take derivative, it is 3x squared plus 3 fifth factorial fifth. This is 5x to the fourth minus, like that. And you can see there's some kind of simplification going on here, because if you look at the factorial 3 means 3 times 2 times 1. So that means you can see this 3 and that 3 you can cancel out. The same thing happened with factorial 5. So because of that, you can simplify this and you simply end up with, and also you can divide by these 3. So one of the 3's get cancelled. After you do all of these, you can see you're going to get 1. And then this is going to be 3 squared now. This is going to be factorial 2 now. This is going to be x squared. And this is same thing. This is 3 to the fourth now. This is going to be factorial 4. And then x to the fourth minus, like that. Now what we can do is we can write this as a uh, new series. So if you use sigma notation, so you can see sigma going from 0 to infinity, negative because there's a sign change, and then you can see this is 3. So you can see these are all even powers. So you can see this is 2n now, and then also divide by the exact same number factorial, and also this is exactly like that. And then at the beginning, when it's a positive, so that means this is going to be n. So that is the uh, Taylor, not the Taylor, the Maclaurin series of cosine 3x. Okay? So it's very easy. Now what we can do is we can simply replace x by x squared, because you can see there's an x squared term. That's what we need. So we can replace x by x squared now. Okay, so let's do that. So we can replace x by x squared, and after that what we can do, multiply by x cube. After you replace, and then you multiply by x cube, because that's what you have in front. So after we doing that, then we're gonna get x3 cosine 3x squared equals to, let's go to the sigma notation and plug in. So actually I can yeah, we can leave this x cube outside, just to make it less complicated. So we're gonna replace x by x squared. So it is n. This is 3 2n no change, factorial 2n no change. But here what happened, this is replaced. So the x, earlier we had 2n, so what we have now is x squared 2n. That's what we have. So this 2 and 2n become 4n now because you multiply, and also you can bring this 3 inside. So that means finally we have this sigma n going from 0 to infinity, negative 1n, 3 to n, factorial 2n, x to the 4n with that 3, so it's 4n plus 3. And remember, earlier this the sine series was as for all, so still it is for all, okay, because you did not make any changes. So that is the Maclaurin series of this new one. So what normally happen is you're gonna use a table. From that table you can find most common ones. You can find sine, cosine, tan inverse, log 1 plus x, or 1 over 1 minus x, 1 over 1 plus x, things like that. And we can use them and use those replacement argument like we did here. We replace one argument to find something you want. So that's the kind of idea. So it's a simple one. Okay, so let's see what else we can do. So as the next step, we can go to this step. So let's say we're gonna find this integral. So let's say find a series, a solution of this integral. Let's say we have this integral x cubed cosine 3x squared dx. So let's say if you get something like that, you can say this is weird. For example, one reason is this is not the derivative of that. So since this is not the derivative, so we can use the substitution technique for this one easily. So this is going to be complicated. So you can use some like other substitution techniques, but the series solution going to be really easy because we already know the series representation here. So what we're gonna replace the function by the series. So we can do this integral. So we can say this is the integral. So we can replace the function by the corresponding series that we just found above. So so we're gonna substitute from this. So that means n going from 0 to infinity. So so let's write this. So negative 1n, 3 to n, factorial 2n, x to the 4n plus 3, the integral dx. Okay. Now what we can do, we can switch the summation and integrate the x term. So that's the only one we can integrate. So we integrate that. So we're gonna get sigma n going from 0 to infinity, negative 1n no change, 3 to n, factorial 2n, and then what happened here is this gonna be x, you can add 1, so it is 4n plus 4 divided by 4n plus 4 plus c, because we still don't know because it's not a definite integral. If it is a definite integral, we do have this c, but since this is not a definite integral, we're gonna get that, and then using some other values we can find what is this c. But for the moment we can leave it like that, and you can see this is a nice series representation of this integral. And you can see also, if you want to simplify this, you can pull this 4 out of the integral. So if you want, you can write it like that, but that's not a big simplification. So we can write it like that, n going from 0 to infinity, negative 1n, 3 to n, 2n factorial, x for n plus 4 over n plus 1 plus c. Okay, so you can leave it like that. So this is like a nice applications of this Maclaurin series. So let's try to do one example how to use the Taylor polynomial. So let's do one example like this. So let's focus on Taylor polynomials now. Taylor, not the Taylor series, the Taylor polynomial. So polynomial can stop at one term. So let's look at this problem. So let's say find the third degree, find the third degree Taylor polynomial of Taylor polynomial of let's say the function fx equal let's say 12x to the fifth square root at let's say a equal 4. So so if you get a function like that, what you can do is just try to find the derivatives, but in this case, a third degree, so you need to find the first 3 derivatives. So we're gonna start finding them. So the function fx, so you can see that this function is 12. You can say x to the 5 half. So we can evaluate this at 4. So if we evaluate this at 4, so you can see this 12. 4 5 half. So this is not that difficult to find. First we need to find the square root, so which is 2, and then 2 to the fifth, that means 32. So this is 12 times 32. So you're gonna get 384. Now go to the first derivative. So it's a first derivative, so which is 12. So once you take the derivative, this can be 5 half x to the 3 halves, so which we can evaluate at 4 again, so which is so 12, so we're gonna get 30 times 4 3 halves. So again, as before, you take the square root, which is 2 8, so 8 times 30, that means 240. And then we're gonna go to the next derivative. So so we have here 30 times 3 halves x 1 half. So f double prime 4 now. So so this can be 45 for 1 half, so which is 90. The 4 1 half is 2. Now the last one is the third derivative. So we have here 45, and then this is 1 half x to the negative 1 half. So this is and then again we can evaluate this at 4. So this is 45 half, and then this is square root. So this is 4 square root, which is 2. So that means you're going to get 45 over 4. Okay, so we find all the derivatives. Now what we're going to do is we're going to plug into the formula. So this is the third degree Taylor polynomial, so it's d3x. So if you plug in for that, so you're going to get f4, evaluate at a, and then f prime 4 factorial 1. This is x minus 4 because a equal 4, plus f second derivative for factorial 2, x minus 4 squared, and the last one is f third derivative evaluate at 4 factorial 3, x minus 4 to the cube, because we are looking for third degree. I mean, we're going to stop at 3. Now what we're going to just plug in the values. We already find them, so we're going to say 240, and then we have 90 x minus 4, because factorial 1 is 1, and then here we have so 45. So the second derivative is yeah, actually we made a mistake, so the first number is not exactly correct. So we're gonna get 384, and then the second number is 240 x minus 4, and then we have The second derivative is 90. So 90 over 2, that means 45. X minus 4 squared. And the last one is, so we have divided, so 3 factorial. 3 factorial we can divide by 3. So that's, you're going to get 15. So 15 over 8 x minus 4 cube. So that's what you get. So you can see, so that is the third degree Taylor polynomial of that function. So so I'm going to give you one example. So you can try this one. So let's try to find the third degree Taylor polynomial of this. So this exercise. So the function is, let's say, 3 square root x. See whether you're going to get this as the answer. So you should get 6 plus 3/4 x minus 4 minus 3 over 64 x minus 4 squared plus so you should get 3 over 512, yeah, 3 over 512 x minus 4 cube. So see whether you're going to get this as the answer for the third degree Taylor polynomial of this function. So you can just pick any function and do this. But you can see these are like a very accurate, because it is accurate up to third degree. So that is the benefit. So you can go any degree you want. So if you need a better accuracy, you can go like higher degrees. Okay, now let's look at several common um, Maclaurin series, and then what we can do, we can use those Maclaurin series to calculate few more things, like few more series and some other application. For example, how to find a limit using those things. So let's look at the several common Maclaurin series now. So these are several common Maclaurin series expansions, and it will help you if you can remember them. And also you can see at the end the radius of convergence. For example, if you look at these three, they are the radius of convergence infinity. That means they converge for all values of x. So that's very important, converge for all values of x. But for the other three, you can see the radius of convergence is 1. So that means you can only go 1 away from the center and each of these. Good. So, and also there are certain other connections as well. So let's look at those connections in the next. So what are those connections? For example, if you look at so the first one, that's the geometric series that we use a lot. That is 1 over 1 minus x, and you can see all the powers of start with 1, all the powers of x. If you go to the second one, there's a relation. What can happen is the relation between the first and the second one, you divide by the factorial. That's the only difference between the first and the second one. So you can see you start with the geometric series. So what happened here is you simply divide by the factorial. Otherwise, it's just the same one, the top one, but you divide it by the factorial. Now, from that, you can actually get all the other next 4. How to get the next 4? So you can see in the next one, you're going to see plus minus sign change, but you only have the odd terms. So there's a plus minus sign change, but you only have the odd powers. Okay, so these are all the odd powers. Okay, and the next, if you go to the cosine one, you can see again there's a plus minus sign change. You only have the even powers. There's a plus minus sign change, but there are all even powers. The EX has all the powers, all positive. Sine has sign change, all the odd powers. Cosine has sign change, all the even powers. Now, how to get the tan inverse? If you go to tan inverse, you can see it is very similar to sine, but you don't have the factorial. So that's the only difference. You don't have the factorial. No factorial. Okay, so the factorial term is missing. You can see no factorial. So that's the difference between sine and tan inverse x. There's no factorial. And if you go to the ln 1 plus x, also there is a relation. You can see it is very close to the previous one, but now you have all the terms. Because in the tan inverse you only have odd terms, but in the ln 1 plus x you also have even terms, but there's a sign change, plus minus. So there are certain relations, and you can see all three start with x. So this one is start with x, start with x, start with x. So those are kind of relations that you can help you remember these common series. Good. But in exam, what normally happens is if you are planning to ask a question like that, you normally get this list. So that's important one. Good. And also the one thing we forgot, this is all odd powers because it's coming from sign. Okay, these are the kind of common series, and the last one is what we call the generalized binomial expansion. And you can see the k is any real number. Here k is any real number. Okay, k is a real number. So this is what we call the generalized binomial expansion. It's very, very useful. For example, if you want to find something like this, 1 minus x squared square root or something like that, you can use this one because in this case k equal 1/2, and you replace x by negative x squared. So you can do that. So that's the benefit of these expansions. So let's try to see a few examples and how to use them. So let's do that next. So we're going to start with this. So find the sum of the series. So let's start with, let's say you have 4, then minus 4 over 3 plus 4 over 5 minus 4 over 7, like that. So if you look at this one, you can see the 4 is common. So we're going to pull the 4 out. If you pull 4 out, you're going to see that it's 1 minus 1/3 plus 1/5 minus 1/7, like that. Now what we can do, we're going to compare this with any of those common series that we have. And for example, you can see that if you look at this one, this is very close to tan inverse. It's very close to tan inverse. So actually, if you plug in 1, this is what you get. So that means this side is simply 4. So this is simply going to be tan inverse 1. Because if you go to tan function and plug in 1, you're going to get that. Because for example, this is a tan series. So tan inverse x is x minus x3 x3 3 no factorial plus x fifth over 5 minus, like that. So you can see that's exactly that. And this x is in -1 x less than equal. So that's the domain that's valid. So you can see 1 is in there. So that means you can plug in that. So that's the reason we use this one. Now we know that tan inverse 1 is pi over 4. So it's a 4 pi over 4. So that means you end up getting pi. So that means if you add this series, you end up get pi. Okay, so this is another way to calculate pi, value of pi, because those numbers are easy to calculate. Good. So let's look at another example. So we can do this one. 1 minus 1/2 plus 1/3 minus 1/4, like that. And then if you look at this one, you can see these are all the terms, plus minus, there's sign change. So this is very close to the ln. So if you look at the natural log 1 plus x, so you see that this is x minus x squared over 2 plus x3 over 3 minus x4 over 4 plus, like that. So that means this is very close to that. So that means this is simply going to be natural log. What you need to do is you can plug in x equal 1. Just plug in x equal 1. So that means this is simply going to converge to ln2. So this ln2, simply ln2. So let's look at one more example. So how about this? Number C, 1 over 1 times 2 minus 1 over 2 times 2 squared plus 1 over 3 times 2 cube, 2 cube, and then minus 1 over 4 times 2 fourth, like that. So if you look at this series, you can see this is also very close to the natural log 1 plus x, but you can see that in this case x is simply 1/2. If we replace x equal 1/2, so this kind of works. So we're gonna say let x equal 1/2 in ln 1 plus x. So if you do that, you exactly get this one. So this is ln, you get 1 plus 1/2. Just put x equal 1/2. So then this is simply ln 3/2. So that's what you get. So it's very simple. This is one of the nice applications of that. So as a final example, we're going to do some problems. For example, you can evaluate certain limits using these Maclaurin series. So let's do a problem like that, evaluating certain limits. So let's say evaluating limits, certain limits. So as a first example, let's do one example. So limit, let's say x goes to 0, ex minus 1 minus x over x squared. So so one way to do this problem is the use because of L'Hopital's rule, because you can see that when you apply x equals 0, you get 0 over 0. So you can use the L'Hopital's rule. But let's use this Maclaurin series argument. What we can do, we're gonna substitute first few terms of the series. We know that ex is all the powers with factorial. So that means it is 1 plus you're gonna get x. So this is x over factorial 1, and then x squared over factorial 2, and then x3 over factorial 3, like that. And then we have minus 1 minus x divided by x squared. And then you can see, you can simplify this. So it's a limit x goes to 0. You can see 1 get cancelled, and then x get cancelled. So you only have the rest left, and then you can also see that you can cancel one of those x squared terms because you have x squared. So from the rest, you can remove a x squared term. So if you remove x squared term, you only left with from the first term. Since you cancel x squared term, you get 1 over square root 1 over factorial 2. The next one you're gonna get 1 over factorial 3, only one x term. Next one you're gonna get a factorial for x squared term, like that. But what happens when x goes to 0? You can see these all goes to 0. All those terms goes to 0. That means you get 1 over factorial 2, which is 1/2. So that's how you can use this Taylor Maclaurin series to find certain limits. So I'm going to give you two examples for you to try. Yeah, so the other argument is use the L'Hopital's rule. So you can use the L'Hopital's rule. So let's try, you can try these as exercise problems. So let's say limit x goes to 0, 1 plus x minus ex over x squared plus 4x fifth. So see what you're gonna do. There's a slight change that you want to make. And the next problem, you can try limit x goes to 0, sine x minus x over ex minus. Okay, so try these two. Again, you can do all these using L'Hopital's rule as well, but let's see how this gonna work. Okay, and then I'm going to give you this problem also. You can do a certain Maclaurin series. So try this. Find the Maclaurin series. Find the Maclaurin series. So let's say the first one is, so you can use the table, 3x cosine x squared over 5. Just go to the cosine, plug in that, and then multiply by 3x. And b, x tan inverse x squared. C, x squared ln 1 minus x. And d, x square root e to the negative x squared. Good. As a final problem, you can try this integral. So evaluate 0 to 1 cosine x squared over 2 dx. This is E and F. Since we know the expansion above, you can do this now. 0 to 1 square root x e to the negative x squared dx. Okay, so try these problems. So these are like really good practice problems. Good. So this is the end of power series review.